And hi, here we are today talking about, or continue talking about our conversation with Newton's laws. Today we're going to discuss pretty much friction. I want to start by reminding us there are four really types of friction. We have kinetic and static friction. These are going to be our main focuses. We also have rolling friction and fluid friction. Now, rolling friction, we are going to examine kind of the special case of static friction. But in reality, rolling friction is the smallest of our frictional forces. Then we have fluid friction. Just very briefly, fluid friction is really anything that is going through a fluid, like a ball traveling through air, a submarine through water, any fluid such as that. Our typical form for our equation is we just have a F equals dv squared, where d is a drag coefficient and v is the terminal velocity. Now the drag coefficient is shape dependent. A ball or baseball has a different drag coefficient than, say, a football. So the drag coefficient is found through differential equations, and we can also find it experimentally. But we have an experimental form of d equals 1/2 c rho a v squared. These things all mean something important. C is our drag coefficient, so C is based on the shape. That's what we just said. Rho is the fluid that we're dropping something through, so our force would be different, obviously, if I was dropping something through air versus helium. And A is the cross-sectional area of our object. Now here I have two graphs set up, an acceleration versus time and a velocity versus time, of what would something look like, a graph or sketch of that, if we were dropping something, say a ball, just through the air. We know if there was no air resistance, that acceleration is going to be constant at 9.8 meters per second squared. However, with air resistance, eventually we reach what's called terminal velocity, so our acceleration continues to decrease until we get a zero acceleration. Now our velocity is going to be flipped. Our velocity starts to get faster and faster and faster until it reaches that terminal velocity point. Notice those two things level out at the same time. Next, I'd like you to turn to turn to example 526 in your notebook, or exercise 526. I've sketched the graph here. I'd like you to read the question. And you can see that my graph, I have the frictional force versus the push force. And we have something funky going on here. We have a nice steady increase. Then we've got this drop and then a absolute steady push force. So what's happening? The abridged version of the problem, we have a 135 Newton block that's being pulled on a rough surface. What we want to know is, for part A, what is the static and kinetic frictional force? Well, at this point here, I see I have static friction, static friction, static friction. How do I know that? It's not going anywhere. And my frictional force, or my general form of friction, is mu, which is the coefficient of friction, times the normal force. So here, as I'm continuing pushing and I'm pushing and I'm pushing, I can continually increase that static frictional force. So I know that static friction happens up until the 75 Newton part. After that, I have a kinetic frictional force, and that's an instantaneous or near instantaneous drop. Part B, they were just asking us to apply this formula of our frictional force, where F is equal to mu times the normal force. So this is just straight calculation. We have a static frictional force of 0.55, a kinetic frictional force of 0.37, and you should see from your calculations that those two things are unitless. Next part is the explanation of the graph. Now, we kind of already did that, but again, I can continue to push an object. This is why the static frictional force is very difficult to calculate, because I can continue to push and increase that static frictional force until it's moving. We'll always notice that static friction is going to be greater than kinetic friction. The last part is, what happens if I increase the weight? I put a brick on top of the block that I started moving. Well, if I increase the weight of the object that I'm trying to grab, that means I'm also increasing the normal force of that object. If that's true, this graph looks exactly the same, except all of my values have to change. I know this because the frictional force is proportional to the normal force. So if the normal force goes up, my frictional force goes up. The kinetic frictional force will go up, the static frictional force will go up. What doesn't change is those constants. Mu is a coefficient that is a constant of kinetic or static friction. So our new values just have a static frictional force up to 150 newtons, and then after that we start getting a push, if I start pushing greater than 150 newtons, I have a kinetic frictional force. All right, so now for an application problem. Let's assume I have a mass that's on a flat plane, and I want to lift that mass, or that plane rather, up to an angle of 20 degrees like I have in my drawing here. What I want to know is that if I have an 80 Newton block, and I know between these two surfaces my coefficient of static and kinetic friction, 0.25 and 0.15 respectively, I want to know as I increase that angle, will the block start to slide? In other words, will it pass the angle of repose? And that is the angle of which I can start to get my gravitational force to be greater than that of my frictional force. That's one way you can experimentally find what the coefficient of friction is. So the first thing I need to find out is, will this block remain at rest, or is it going to start to slide down? So I drew my free body diagram, and then I added my components. Now I don't quite know yet if I need this push force, this orange force that I've labeled FP. That would be the, if my block is going to slide, the force I need to hold it up. So I have my free body diagram, I have my components with F parallel and F perpendicular, and then the things that I know my perpendicular component of gravity is mg cosine theta. I know my parallel component of gravity, mg sine theta, and my static frictional force, because it's not moving, mu s times the normal. Come all the way back over here, we're going to apply Newton's laws. I know my net force equals ma, and I know the acceleration wants to be equal to 0, especially in the y direction. Notice I do have an axis here. So I know the normal force minus my perpendicular component to gravity is 0. So I know that the normal is equal to mg cosine theta, again pulling that from my perpendicular component. Now, if it's at rest, the static frictional force in the x direction needs to be equal to F parallel. Easiest way to do it is just check them out. Plug in first my static frictional force, mu times the normal. Now this is why I wasted my time, I should say, with the y direction. We know nothing's happening in the y direction, but I knew I needed to find my normal force. So the static frictional force is mu, which is my constant, times the normal, mg cosine theta. That, because my normal force is equal and opposite to that perpendicular force, I get a static frictional force of 18.79 newtons. Next, check to see if the parallel component of gravity is equal to that. F parallel I know is mg sine theta. That comes out to 27.36 newtons. So I know my block is sliding down. So what do I need to do to hold it? To hold it, I need to sum all my forces. The push force plus my static frictional force minus F parallel, that's all based on my free body diagram, has to be equal to 0, which means I need to apply a force of 8.56 newtons back up the ramp. Now I'm not sure if you can see this, so I continue to say, what is the max force needed to just to just keep the block from moving? In other words, I want to push, and then finally just start pushing. In other words, until I overcome static friction and the gravitational force. Remember, based on that graph we saw before, as I increase my push force, the static frictional force increases until it can't hold anymore, and then I start to move. That's what we're looking for here. So what you can see is I have a different free body diagram. Now I have the static frictional force pointing down, because by definition, the frictional force is opposite the direction of intended motion. And now I'm applying enough force to try and break that friction. So the static frictional force flips back down the hill. F net equals ma. Now my components are me pushing up. Everything else is coming back down. Subtract out the static frictional force, the parallel force. I want it to be equal to 0 because, again, it is that instant before it starts to move. So I'm not accelerating yet. My push force, adding all my components, I get a push of 46.15 newtons. My last question is, if I continue to push at that rate, the block is going to accelerate. I want to know what that acceleration is. The free body diagram remains the same because my static friction is still opposing motion. The only difference now is I have the exact same formula as I did up top. My only difference is instead of static friction, I'm using kinetic friction. So I have the push force minus kinetic friction minus the parallel force equals ma. Rearrange, solve for a. We get an acceleration of 0.92 meters per second squared. I hope this was informative. If you like it, if you comment, I don't remember what I'm supposed to say, but like, share, comment, subscribe.